Hi guys. In this video, I would like to show you how to estimate the population mean and population variance simultaneously for some real data set. And this is a real case that is, most of the time you don't know mu and you don't know sigma. So how do I estimate both of them simultaneously using the Gibbs sampler? But I will show you the code for the Gibbs sampler. But in another video, I will show you how to use a package in R. So let me have the library read X, and then you give the path of the data on your computer. The data will be uploaded on Canvas, so you download it, and then you download the R code, and then you practice on the R code by uploading the data set and then work on it. So now I read the data, I make it in a data frame, and then let's see the head, the first 6 observations of each variable. The first variable is taxes, the second one is bedroom, third one is passes, price of the house, size of the house, the lot size, and so on. So this data set has many variables, but let's say we are interested in price, and we are interested in calculating the mean of the price and the variance of price simultaneously. In the frequency approach, you calculate the average of the price, the sum of the values divided by n, and you to calculate the variance, you use the formula that sum of yi minus y bar squared divided by n minus 1. But in Bayesian approach, we work in a different way. So let's use the price divided by 1,000 to make it nice numbers, but you can keep it, it's up to you. So let's divide the price by 1,000, because I don't like the mean to be very big and the variance to be very big and so on. So this is the mean y bar, and this is the variance s square using the frequency approach. And let me graph the histogram, and let's see the to feel with your data. This is the histogram of the prices, right? The prices of the houses, and this is the number of values we have. Let's see how many observation in our data. We have 100. So for each house, we measured these, how many variables? 6 variables. The first step, you need to assign prior distributions. So let's assign prior distribution for the mean and the prior distribution for variance. Let's assign Jeffreys prior for the population mean. The Jeffreys prior for population mean is normal with mean 0 and variance big value. It means much variability. It means less. It means much uncertainty, less information. So let's use mu 0 as 0, and sigma 0 square is 1,000. And also let's use non-informative prior for the population variance. So use inverse gamma with a very small value for alpha, very small value for beta, which is open box prior. So alpha is 0.01, beta is 0.01. And then I will randomly select 20,000 of values from each posterior distribution. So number of iterations is 20,000. I will not use all of them. I will ignore some of them if the convergence didn't happen. But if the convergence happened from the beginning, you can use all of them. I will save the generalized value from the posterior distribution of the mean under name gen.mu. And I will save the sample generated from the posterior distribution of the population variance under this name. So have this one. This one. And let's start by initial values. You can start by initial values for mu, any value, whatever negative or positive. You can start initial values for sigma square, but any value, but should be greater than 0. So I will start by nice values. I will start, or I choose the initial value of mu as y bar. Initial values for s square is s square. Or the initial values for sigma square is s squared. Those are nice initial values, but you can start by anything. So let's store the first one as the first value. Store the first value, the s square as the first value, and the sigma square and mu. And then starting from iteration 2, because on iteration 1, we have these two as initial values. So given this one, I will randomly select value from this distribution of sigma square. Given sigma square, I will generate a random value from the posterior distribution or the conjugate posterior conditional posterior distribution of mu. So let me explain this one. So mu randomly select from normal only one value from this mean and this variance. So the mean is this one divided by this one. This is the mean in our lecture note, the posterior mean in our lecture note in terms of tau square. So it is tau square times the sum of y. Sum of y actually is n times y bar. So I make it sum of y. Times the tau square plus tau 0 square plus mu 0. And at the bottom, we have n tau square plus tau 0 square. So this one divided by this one gave me the posterior mean of the population of the conditional posterior distribution of the population mean. And 1 divided by the square root of this one is the posterior standard deviation of the, or the standard deviation of the conditional posterior distribution of the population mean. And for the population variance, alpha is n divided by 2 plus alpha, the prior alpha. And the posterior beta is the sum of y minus mu square divided by 2. This one is ny. This one is ns square, because sum of y minus mu square is n sum of square, ns square, divided by 2 plus beta. This is the posterior alpha, posterior beta. And then I will randomly select a value from the gamma distribution. And then I will use 1 divided by, it gave me a value generated from the inverse gamma. So if you'd like to use inverse gamma function, it's fine. If you'd like to use 1 divided by gamma, is fine. And after we randomly select one value from mu and randomly select one value from sigma square, these will be initial values for the next step. So let's do it many times. Like how many times is 20,000 of times? And let's wait. This is this trace plot for mu, and this is a trace plot for sigma square. The y label should be sigma square is better than s square. This one should be sigma square actually. So I see the convergence happen because it looks like it is randomly scattered about some value like 120 plus, and this one is randomly scattered about some value like this one. So this is a trace plot, looks like the convergence happened. So now let me graph the posterior distribution of mu, posterior distribution of sigma square, posterior distribution of sigma, and look at the histograms. Those are the 3 histograms: the histogram of mu, the histogram of sigma square, the histogram of sigma. And now let's summarize these 3, the 2 posterior distributions, the posterior distribution of mu and posterior distribution of sigma square, and both the summary in a table. I'm going to calculate the posterior mean, posterior standard deviation, and 95% credible set. Those are very important. In a table, I create a table first. I give a name for the columns for the table. The first column is mean, second column is standard deviation, third column is 2.5 quantile, last one is 97.5 quantile. And the rows are 2 parameters we are interested in, mu and sigma square. And then I will fill in the table by the mean of the posterior distribution, or the mean of the population mean, the posterior mean of the population, and the posterior standard deviation of the population mean, the first quartile, the third quartile, the 2.5 quartile, and 97.5 quartile. Let's do the same thing for sigma square, and then round the values. This is the numerical summary. I see the posterior mean is 122.65. The standard deviation is 5.62. The lower limit and upper limit of the 95% credible set is 111.39, 133.64. And the posterior mean of the population variance is 3256.01. The standard deviation, the 95% credible set. So this one means with 95% probability, the population mean is between 111.39 and 133.64. And with 95% probability, the population variance sigma square is between these two values. If I would like to calculate p-value, like for example, maybe I'm interested in testing H0, the population mean is greater than 230, or the population mean is less than 230. I can calculate the probability of greater than 230 using the random sample. It is the mean of generated mu samples greater than 230. It will count how many value in the random sample greater than 230 divided by the total number of values. And this one will be the probability of H0. The probability of H0 is 0. It means it is less than 230, because for sure the other probability is 1, exactly 1. It means for sure the mu is less than 230. So you can work with the random sample. You can do whatever you want. You can do estimation, inference, whatever. So now we learned how to find the random sample, generate a random sample from each posterior distribution using the conditional posterior distribution. This is the idea of the Gibbs sampler. If you have any question, please let me know. Thank you. See you in our next video.